Chapter 5, Filtering. In this chapter, we're going to discuss a series of topics pertaining to filtering in the observation domain or in frequency domain. The topics are distinction between signal and noise. We're going then to talk about filtering in the observation domain or the data domain, and here we can use the idea of either observations spatially distributed or distributed over time. Then we are going to discuss the idea of sequential adjustment as a precursor to Kalman filtering. And Kalman filtering is a very important technique today, and it is very useful for us to have a good understanding about the mechanics of Kalman filtering. If you understand the mechanics of Kalman filtering, we can understand any of its flavors. And finally, we're going to talk about filtering in frequency domain. So we're going to go into the discussion of spectral analysis and how we use these frequency characteristics of data sets to separate from signal and noise. The learning objectives of this chapter can be stated as follows. At the end of this chapter, we should be able to summarize the main characteristics of filtering data, explain the major characteristics and mathematical formulation of Kalman filtering, explain similarities and differences between Kalman filtering and step-by-step adjustments, summarize the characteristics of spectral analysis, and choose filtering tools to various situations in geomatics. So it is interesting just to look at this figure that tries to show meaning of three terms that are commonly encountered: filtering, smoothing, and prediction. Filtering can be seen as whenever we get an estimate at the very end of the data set that we have. So let's consider the horizontal axis here representing time, and we have collected data up to this epoch t, and then we use the data collected up to epoch t to get an estimate at epoch t. Of course, if more data is observed, the span of data will grow towards the right, so we have more data, and we are going to get the estimate at the end of the data. Okay, smoothing is when we use the data set and we can have an estimate based on the data set at any time during the period that the data was gathered. And prediction is essentially when we get an estimate outside of the span of data. So here is the definition that we just described, and you can have a look at it. It's essentially repeating what I said. Filtering, if the time at which the estimate is desired coincides with the last measurement point. Smoothing, if the time of interest is within the span of available data. And prediction, if the time of interest is after the last available measurement. Now let's look at filtering. As a matter of fact, you're going to realize that we have been doing filtering that as a matter of fact, least squares adjustment is a filtering process. How can we define filtering? Filtering may be defined as a process used to separate signal from noise. And we know very well from the discussion on trend analysis that signal is anything that we have interest, and noise and is anything that we have no interest. Now the input data will contains both signal and noise. The separation between signal and noise, namely filtering, is carried out as a function of frequency, of the frequency characteristics. So even if we are doing filtering in the data domain, we are using this property of the data, because there is the difference in frequency content or spectral content of the input data. The filter lets the signal pass through a frequency band and stops the noise which is outside of this band frequency. So which means the filter lets what we are interested in go through, and it blocks what we are not interested. So here is a very simple diagram about filtering, but it represents what it is. So we have the input data that contains signal and noise. So it's all the information would be well mixed up, and then it goes to the filter, and the filter separates what we want from what we don't want. So we can think of a coffee filter that will have the input data is basically the water and the coffee powder, and what is going to be the output, the signal, will be the coffee that we can drink, and the output will be the leftover that is in the filter. Now, of course, that there are some people that would prefer to eat the coffee powder, but that's okay. So it just emphasizes the idea that what is the signal and what is the noise. I usually also use this funny analogy of a factory of sausages, that the input is the pig and the output will be the sausage. The noise will be everything that is left over. As I said, we have done filtering so far without really telling it. The process of least squares adjustment or least squares approximation can be regarded as a filter. So we are writing down here the equations for the parametric case of adjustment and for the least squares approximation. And what we can see in here is as follows. We have our input data. The input is right here. This is the misclosure. Okay, that's in the non-linearly, in the linearized parametric case. And here is the output. The output is a correction to the approximate values. So all this quantity here is actually a filter that is separating the signal, which are the least squares correction vector, from the noise. And what is the noise is actually the residuals. here we have the approximation. So what approximation is doing? It is from our input data L, it goes through this filter that will give us the signal, and the signal would be the least squares coefficient of a generalized polynomial from the noise, and the noise would be again the residuals. So we can actually use hat in all these quantities here. So okay, so what we have in here, all these equations, all these arrays, they put together, they represent the filter. So in least squares, what our noise will be essentially the residuals, and our signal will be the parameters. At the end will be the parameters, the estimated parameters, or the estimated coefficients. So therefore, filtering, least squares, adjustments, least squares, approximation, they are a filtering process. Now, we use digital filters, and digital filters are a consequence of the development of microelectronics and computers. The input and output, they are a sequence of discrete samples picked up from the continuous input signal. So applications of digital filters in geomatics are various numerous. We have a filtering that can be done inside the instrument, or filtering that can be done on the data that is collected by the instrument after the internal filtering process takes place. So, for example, equipment such as GPS receiver and digital echo sounder, electronic theodolite, or EDM, they all have internal software that will make a pre-processing on the signal, on the original input. So, which means that the output from receivers, they have already gone through a certain filtering pre-processing, but they still contain signal and noise. And then we have these output data that then we can basically do our own filtering. So, for example, have tidal records, which contains the tidal information of several frequencies in photogrammetry, remote sensing, GIS, etc. So, in our professional careers, most of us will be dealing with filtering of data as collected by the receivers. Only those of us who may end up working for equipment manufacturers will be involved with filtering that is done inside the receiver, unless we're building our own receiver or anything like that. But anyway, and often in geomatics, we are interested in the low frequency part of the input. Okay, in most applications in geomatics, we're using a so-called low pass filter. So our signal is the low frequency part, and our noise is the high frequency part. And that becomes clear when you look at a plot of the estimated residuals. The estimated residuals are never smooth. Okay, they will be they will show higher frequency variations. We typically deal with linear filters. We can say that a filtered series L prime is a linear function of the original series because the original series goes through a linear filter. A linear filter is basically a matrix, and we have different types of linear filters. We have the convolutive type and we have the recursive type. So the convolutive or non-recursive linear filter is basically something that will be the input data goes through a linear filter, and we have now the filtered data. The recursive type is when the input data goes through several filters, through a sequence of linear filters, or linear filters are applied recursively to the input data. So we have these different number of filters here until we have our signal or filtered data. Here's an example of sequential filter. We are trying to imitate here what the matrix, the arrays will look like. We have here an array that contains all the observations. Okay, so we have from L1 all the way to Ln, and the sequential filter will essentially be composed of the first rows of the linear filter will be composed of zeros, and also the last rows of the sequential filter, of the linear filter, will be rows. So in other words, we are going to have in our filter data only the middle of this array will be composed of filtered data. The beginning of the array and the end of the array, the vector, corresponding to these zero rows of the linear filter, they will be zeros. Okay, they will be zeros. So this is a characteristic of sequential filter. We're going to work on examples, and you're going to see that very clearly. Another type of filter is the predictive filter, in which case here we have our observation vector, again from L1 all the way to Ln and observations. And what we have in here is essentially the filter matrix. The first rows, its first rows will be composed of zeros, and as a consequence, we also be having the first arrays in the filtered data will be zeros, and the rest will be composed of the filter data. We can also talk about memory of a filter. A filter is known as a fixed memory filter when all observations are equally weighted, and we take only those in an interval delta t into account, or a moving interval. I'm referring here to moving interval because the example of a fixed memory filter is the so-called moving average filter. Expanding memory filter is when the observations are equally weighted and we take into account all observations within a growing interval. So the difference, if you look at the fixed memory and expanding memory, the difference between them is that the fixed memory will work with intervals. This interval delta tau, okay, and this is for one group of observations. Now another group of observations that will result another filter data, delta tau. You see these interval delta tau is how to call is constant. The expanding memory, on another hand, we have this is the original interval for the data that we're filtering, and then we basically will be adding additional observations. So delta tau was this interval here. Now we have another delta tau. The delta tau becomes all that. So delta tau is growing in size. Then we have another delta tau that we now are incorporating these observations here. So delta tau, the first delta tau is just this piece here. So the second delta tau is this piece in here. The third delta tau is this piece in here. So what is happening is that our interval is growing. So which means that the memory of the filter is expanding. Example, we have Kalman filter and the bias filter. And we have the fading memory filter. When we apply a weighting function that decreases the weight, the further in the past the observations are. So it would be something like that. So this is the interval delta tau. This is a time t. And what happens that the observations at the estimation time, they will have heavier weight, and the weight for the past observations will decrease until at a certain time interval they all go to 0. Okay, and of course that these shape, the shape that we have, will keep moving for the for another filtering that we have. It's going to be something like that. Okay, the same delta tau, but the last observation is this one here now. Example, recursive filters. Depending on what type of signal we want, we will have different filters. If we are interested in the low frequency, only low frequency, it means that our filter will let the low frequency information go through and will block all the rest. We call that a low pass filter. On the other hand, low pass filter. On the other hand, if you are interested in the high frequency, our filter will let the high frequencies go through and it will block the low frequencies. Therefore, we have a high-pass filter. But what if the information that we're looking for is in the middle, is in the intermediary band? We don't want the low frequency information. We don't want the high frequency information. In this case, we have the so-called band pass filter. So only the intermediary frequency or a band, a preselected band of frequencies will be let go. So for a low pass filter, the signal is the low frequency and the noise is the high frequency. For a high pass filter, the signal is the high frequency, the noise is the low frequency. And the band pass filter, again, we are interested in the intermediary frequencies. The low and high frequencies are the noise. So we are going to break the video lecture now. And what the next one, we're going to start to look at examples of filters, and we're going to set up some data set, and we're going to look at this data set in such a way that we can understand the how these filters they work on these data sets. So talk to you soon.